Doing well. Now we are going to start the second part of the course, and this course is this part is devoted to understand the theory of multiple integrals. Okay, we already know how to integrate nice functions like continuous functions which are defined on R or on an interval in R, correct? So that now we have the situation where functions are defined for 2 variables and 3 variables and so on, correct? So we are going to develop an analogous theory of integration, and when we have 2 variables we will call it double integral. When we have 3 variables we call it triple integral, and the general term is the multiple integrals. Okay, so we are going to slowly start and then pose analogous questions which we are aware of from the calculus 1 course, and we will see in the process that this process of integration will up to a point you will see that it is like almost parallel to whatever we know, and then it has some nice geometric features which will help us, and they were not there when we were studying integration for one variable. Okay, so in general you all of you know that integration is basically about finding areas and then the volumes and so on. So in this course now, since we can deal with functions of 2 variables and 3 variables, we will see that if I take a nice surface in R3, that means the graph of a function, then we can talk about the area, and the integration will help us in doing that. And similarly we can measure the volumes and so on. Okay, and when we do this, there will be definitions of how to do it, but then we also have to develop the practical tools so that we can compute. Okay, sometimes just the definition may be very difficult to go with if you want to really compute certain things. Okay, so we will also see that how to use the knowledge which we already have from our calculus 1 course about the integration. Okay, and then the most important part in this section is going to be this fundamental theorem of calculus. If you recall, for one variable you had this theorem, and in the later part of this course our goal will be to develop an analog of this in higher dimension basically. Okay, so slowly we will build up the theory. Okay, so this I have just taken it just to recall you guys that what the integration was, or what was the idea of Riemann integration. Okay, so you start with non-negative, and I am assuming continuous function. Okay, and this function is defined on this interval a to b including the endpoints. Okay, so this is a closed and bounded interval, and so this is a function. So this thing over here, this is nothing but the graph of the function f on the interval a to b, correct? So what is the integration of f? It basically gives you the area which is above this interval a to b and under this curve, isn't it? So how do we find it? Okay, and if you just try to recall, the problem here is because this curve has got these bends, correct? This is not flat. If it was a straight line or a combination of lines, then we know how to compute it, correct? Because we could have just found the rectangles, but the problem is this is bending like at almost every point here. So we have to take into account this curvature, okay, while we are trying to compute the area. So what we do in any subject, you will see this is the fundamental idea, that there are certain things which are kind of given, okay, given by nature, or we kind of have some intuition to do that. So when we are talking about area, we are talking about length and the width. So we know that if a piece of paper or piece of a field looks like a rectangle, I know immediately what is the area, because it's going to be the length multiplied by the width. Okay, but here there is no clear width, because at every point there is a height is changing, correct? So what we are going to do, we are going to use what we know, okay, and we see that how far we can extend it, and this is where the mathematics or the technicality the analysis comes in, that the known idea, how far we can push it so that we can understand more about nature, or about things which are not immediately given to us in a way. So this is what we are going to do. So what we are going to do, we know that how to measure the area of rectangles. So we are going to approximate this region, okay, this region by rectangles, because once I have rectangles I can compute their area, sum them up, I get something, okay. But the problem is, you see, each rectangle here is not really giving the area which you want. It is sometimes giving you more, sometimes it is giving you less, or in some parts are left out and some part are extra added here, isn't it? So this process, but immediately it suggests us, if we are a little bit open, then we will understand that, you know, if I make the size of this rectangle smaller, then this error part, which is more or less, both are the errors, correct, that can be minimized. Because if I, for example, if I take this one, then, you know, I don't have to consider this part, the rectangle will become like this, okay. So this is the underlying idea here, okay. For example, this one I am saying, yeah, drawing is little bit technical all the time here. So what I am saying is, like, you know, if we keep on taking smaller and smaller rectangles, then the error becomes smaller and smaller, okay, because we get a nice approximation. But you know, this process, if we say smaller and smaller, that means it is becoming larger and larger number of the rectangles which we are considering, okay. So eventually we are going to get I mean, you know, something called the limit, okay. So this is what we do when we had defined the Riemann integration, that we take or we decompose this a to b interval into smaller pieces, and generally we do it equal length. So this we have you know, written as delta x. So you divide this big interval into smaller intervals, and where each sub interval is of length delta x, and then look at the value of the function in this each interval, and then you call that height and consider this rectangle. So this is what is happening. So this is what we do, correct. We consider the values of f and then multiply by the width of the interval, and then this is going to give you the area of each rectangle, and you sum them up. So you are going to get an approximation, but then you have to make them smaller and smaller so that the error is minimized. So that means we take this n goes to infinity. So this really, you know, converts to this region, this whole thing, okay. But here there are several technicalities. One has to you know, because this side you are summing and this n is becoming large, so you have to make sure that things do not go to infinity, and you know, this limit makes sense, okay. So all that has to be done carefully. But if you remember, if we assume that function is continuous, then one can show that this limit exists, and so on. So this is the idea which was the fundamental to you know, consider the area of regions which were not really given by two straight lines, or they were not looking like a linear combination of rectangles, okay. Rather there was the curvature involved, okay. So we are going to you know, extend this idea to take into account you know, the situation which we have, okay. So let us look at right now functions of two variables, okay. And as usual, we will first consider the non-negative function, and we consider the domain to be the rectangle, okay. So this is the immediate analog of an interval. So an interval in R has the analog in R2 as the rectangle, okay. So we consider this simple situation, and what we want to consider this is the graph, or this is the surface of the function. So what we want to compute now, we want to compute this volume. Now this is a picture in R3, okay. I am given a function defined on this piece of rectangle, and this function is nice, continuous, and so on. So you see that in R we had a curve, and then we had we wanted to compute the area under that curve, okay. So now the situation is that we have got a surface, okay, and it is defined, the domain is a rectangle, okay. So it looks like a square, but you know, it can be rectangle. The AB and CD they can be different numbers, all right, and the length can be different, okay. So this is the notation we will always use. This solid, okay, under this curve and above this region R is always going to be denoted as S, and our target, our goal is to find the volume of this, okay. Again, you see that if the top part was flat, then this is like a box, and we know all the dimensions, we could compute the volume, but that's not the case here. So we are going to use the same idea. What we are going to do is we are going to approximate this solid by smaller and smaller boxes and then sum them up, take the limit. Okay, so this is what the underlying idea here. But here of course things will be a little more complicated because you will have more than one things to deal simultaneously. Okay, so this is the idea of double integral, because as I said there are two variables involved here, so the integration is going to be in two variables. Okay, so we call it double integral and over a rectangle. Okay, so consider the situation which we just discussed. Take a nice continuous function on R. So what we do, we need to divide this rectangle like we did in the case of real line. We divide this rectangle into smaller sub-rectangles. Okay, so how do you do that? What you can do is you can divide the interval a to b and divide the interval c to d into smaller sub-intervals, and then their product, the Cartesian product, is going to give you rectangles. Okay, so we do this, we exactly do that. So we divide this interval into sub-intervals of equal lengths, call that delta x, and this, if there are m sub-intervals, the delta x is b minus a by m, and similarly you divide the other interval, okay, which is the limit for the by variable. Okay, and you divide it into n pieces with equal length delta by. So what we get this m times n, correct, because there are m on the x-axis and there are n on the y-axis, so the number of rectangles are going to be m times n, and the area of each Rij, I am calling it Rij, correct, the rectangle, the smaller one, is going to be the length and width, and length is this and width is this, correct. So this is delta A is written for the area. Okay, so the area of a smaller rectangle is delta A, and as earlier what we do, we take a point in each rectangle and consider the sum. Okay, now I have to be careful, there are two sums involved here. Okay, and so this is what, this is the height, the height is decided by this value of the function at a point inside that rectangle, and this is the area of the base. So what you are going to get, this is the volume. Okay, this is the volume of this box. Okay, so basically above this each sub rectangle we are going to get a box. Okay, and we are going to put all these boxes together and find their volumes and sum them up. Okay, but as earlier, because there is a curvature involved, this is not a flat situation, so we are going to have a lot of errors here. Okay, so we have to keep subdividing these rectangles, make them smaller and smaller, and then these errors will be minimized, and then take the limit. Okay, so one word of caution here, that here we are talking about double sum and then double limit. Okay, so you guys have to be careful. Okay, if you have not done these kind of problems where you have to deal with double sums, then discuss it during the tutorial or office hours. Okay, so what is the meaning of convergence when there are two parameters and so on, so please discuss that. And we say that, okay, this limit is the double integral of f, and this is the notation for that, over R. And of course, I mean, we can make sense of this only if this side, this limit exists. Okay, so whenever this limit exists, we say that the double integral of f over R exists. Okay, so far we have not said any for what kind of functions we will have the limits, existence of the limit, but I am going to leave it because the idea is essentially the same which you already know for functions of one variable. Okay, so there are certain terminologies. The sum over here, this is called double Riemann sum. Okay, the word Riemann is coming from the Riemann integration, and we will not write this double again and again, we will just refer to it as Riemann sum. And so here we have taken, as I said, you take a point, so this point you can take anything, you can also take it to be the midpoint of Rij, the center, or you can take on any boundary, and it doesn't really matter because eventually we are going to make things smaller and smaller. Okay, and this term dA is the integral. In the integral above is, this is the smallest this small area, correct, so this, which is going to go to 0, and sometimes we will also write it as dx dy, because that is the infinitesimal length and then the width, correct. And as I said, if the limit exists, we say that this double Riemann integration, but double we will not write again and again or even refer to it. So we say that this function is Riemann integrable. Okay, so if this limit exists, then f is said to be Riemann integrable over this rectangle. Okay, so this is exactly a parallel idea from your calculus 1 course. Okay, so you should be able to relate to it, and if not, just recall some of the definitions from your Riemann integration. And here the definition is almost the same, except that there are more than one variables over here. Okay, and as I said, the double integral, it gives you this volume of the solid S, which is under the surface and above the rectangle. Okay, and all those properties which you can think of for integration, they will be true over here also. Okay, because this is defined in terms of summation. Okay, and taking sum is a linear process, so immediately you will get that the double integral is a linear process. Okay, and one word of caution again here, I had defined the integration only for non-negative function, because we wanted to relate it to the volume of something. So we take something which is non-negative because that should be giving us the height, but the idea of integration can be extended to any real valued function, provided of course that limit exists, or in other words, that function should be Riemann integrable. Okay, so what you can do is, this you could have taken in the definition itself this f to be real valued continuous function, but if you don't want to do it, first you want to do it for non-negative functions, what we can do is that any real valued function can be written as sum of or difference of two non-negative functions. Okay, and for each non-negative function you can define the integral, and then you just define the integral for f via this. Okay, so this is the way you slowly build. Okay, this is the meaning, that you do you try to define things for an easy situation, and then from that easy situation you move on and incorporate more and more objects into your definition. Okay, so as I was telling you, for what kind of functions the double integration is going to make sense, or what kind of functions are going to be Riemann integrable, that one can do in a similar way as you do in your calculus 1. So for example, this theorem can be proved that if f is a continuous function, okay, defined on a rectangle, then it is Riemann integrable. Okay, so what I am saying, that that limit of double sums will make sense when f is continuous. Okay, and not only that, in fact this is how you start proving in calculus 1 also. First you show that continuous functions are Riemann integrable, and then you see that if the function has got a discontinuity at a point, or then finitely many point, then they are also Riemann integrable, and the same thing is going to happen over here also. Okay, that so here finitely many points, they will become finitely many curves. So if your function has got this kind of finitely many discontinuities, then also one can show using exactly the same idea that your function is Riemann integrable. Okay, but in this course our emphasis is not really going to be on developing these properties of Riemann integration, because those are completely in line with your calculus 1 course. Okay, so rather what we are going to do is we are going to use it to compute certain volumes and certain surface areas and so on. Okay, so that is mostly we are going to talk about different kind of problems in this course, rather than just proving those properties. All right. Okay, so yeah, as I was telling you, this was the situation for double integral, and the same thing, exactly the same thing can be extended to a function of 3 variables. Okay, so that is going to give you the notion of triple integral. Okay, so this is precisely the same idea. You start with now a box. The domain is going to be in 3 variables. So the analog of rectangle is going to be a box. Okay, so the domain is a comma b cross c comma d cross r comma s. Okay, so there are 3. So this is a box, and you start with a nice function f, and then you consider this triple Riemann sum. Okay, so this del v here is going to be the volume, okay, of the smaller box. When you write down this big box into smaller boxes, and you do the exactly same process, then take the points, and you say that your function is triple Riemann integrable, and the notation will be this if this triple limit exists. Okay, so this is exactly the same idea, so I will not really talk much about it, because this is precisely the same idea, just that we have one more extra variable here. Okay, and this dv is the volume component. Okay, and it is also written like this. So all the properties which I just said for double integral, they are going to hold for the triple integration also. All right, so we have to just look at this definition, for example. Now this definition of triple integral or of double integral, this looks like too much of work if you have to compute the volume, isn't it? Because first we have to divide it into smaller pieces, and then evaluate these volumes of smaller regions, and then put them together and then take the limits. Okay, so if we have to use this to compute volumes, it's going to be cumbersome task. Okay, so rather what we are going to do is we are going to develop some theoretical notions or some theorems which will help us, or which will provide us with some tools. Okay, so that we can use our theory of integration for one variable, and to immediately find some integrations for two variables and three variables. Okay, so this is what we have to do, because applying this definition and computing the integral is going to be extremely difficult task. So we have to do in calculus 1 also, we don't apply this definition to compute integration. Rather, we had proved that theorem which we call the fundamental theorem of calculus, and that was such a big tool to compute the integrals, isn't it? So we are going to do something similar here, that we are going to make use of that single variable theory, and we say that how to compute double integrals using that, and then triple integrations using that. Okay, so this is what we are going to do, and yeah, this is precisely what I think I have written over here. Yeah, whatever I just said, it's written when you go back and read it your own. Okay, so this idea is basically going to give us this notion of iterated integrals. Okay, iterated, you can understand this term because this we did for differentiation also. The idea is very simple. Now you have got two variables. Okay, and we are integrating a function of two variables or three variables. So can I do it variable by variable? So this is what the idea is. If we can do that, then at a time we have to consider only one variable, and theory of one variable we know quite well. Okay, so this is the whole point. Okay, so you consider the same situation. You consider a function defined on a let's say on a rectangle. You could do this over a box also for three variables. So I will do it for rectangle, you do it for box. Okay, and what you do is for each fixed x, you think of this as a function of bi, and then integrate, and then whatever you get, that is going to depend on x, and then you integrate whatever you get with respect to the remaining variable. Okay, so this process we have to continue. Okay, so what I am saying here, that they think of this function as a variable bi, and then we can integrate over bi. Okay, so when I say we can integrate, one thing we are kind of assuming that the integration makes sense. Okay, so that is, I see, if it doesn't make sense, whatever we talk about is completely out of the question. Okay, so same thing we can do, and keep bi fixed and then allow x to vary and integrate over there. And in this process, so for example, when I am integrating with respect to bi over c to d, this quantity whatever I get is going to depend on x, so call it a function of x. And now this be integrated with respect to x, and I get this. Okay, so I have put here bracket, that means I am first performing the integration with respect to bi, and then with respect to x. Okay, this is something this is not part of the equation. Okay, so just erase it. Okay, so such a thing is called iterated integral. Okay, that means the function depends on more than one variable, and you are integrating it one variable at a time. okay, and then keep on doing this process. Okay, so this is the process which gives you iterated integrals. So when you have two variables, you are going to get two types, because I can also reverse, I mean switch the order. I could have done x here and then by here. Okay, so that is going to give you another one like this one. Okay, so okay, as I have been telling, please define the notion for three variables also. Okay, but once I do this, we started with defining double integral, okay, over a rectangle without going into any single variable. Okay, and now we have defined two more things, the two iterated integrals, and I'm just going to tell you that this it looks like that this is going to give you the same thing. Okay, so we have these questions with us, that these two integrals, are they same? Are they going to give you the same quantity? If not, can we have some conditions on f so that they are equal? There's small typo again here. Okay, and suppose both the iterated integrals, they make sense, they are equal, then are they going to give us the same value as the double integral? So these are the natural questions you would ask. Okay, and it so happens that for many nice situations we get that both these guys are same and they give you the value of the double integral. Okay, and that helps us in computing these double integrals. Okay, so it's a theorem, it's called Fuvini's theorem. Okay, now this theorem doesn't have a counterpart for single variable functions, because this needs at least two variables. Okay, because we are going to talk about iterated or changing the order of integration. Okay, so I think in the previous slide somewhere I must have said that I will not put these brackets. I would rather write just the integrals. So from the left you are moving, that means this is considered at the end. So what you should be thinking is this dx is done first and then the dy. Okay, so that way you have to keep in mind, because the brackets becomes in a way they take up some space, and this is more neat notation. Okay, so what does it tell us? This theorem tells us that you take a continuous function, okay, real valued continuous function, and defined over a rectangle, like the situation we have. Then this double integral which we had defined, okay, I know what is the meaning of double integral, is precisely these iterated integrals. Okay, you can compute as per your convenience any one of the two, and you have this double integral. Okay, so this is a very powerful theorem, very powerful theorem for higher dimensions, okay, in the integration theory, because it brings down your higher dimension to lower dimension, like dimension 1. So at a time you are only worried about one dimension. Okay, so this is a very powerful tool. Okay, and this is the beauty of the theory, because it gives you these tools. Sometimes people say, like, one should do applications all the time, and then theory is useless. But without theory, how do you simplify the situations? So you have to have a balance between the two, that theory is important, and then one should know how to apply it, both the situations. Okay, so here I have said f is a continuous function. So I must tell you that this is not the most general form of Fuvini's theorem. Okay, Fuvini's theorem holds for more general functions here, but that is not really the concern in this course. Okay, because that is really technical, and in fact even the proof of this is little technical. So I mean this course doesn't really involve the proof of this course. But of course, if some of you are interested, you are most welcome. I can teach you the proof. All right. But what we are interested in, how to use it, this idea. Okay. So here I have written like small exercises. Okay. So the theorem need not hold for all bounded functions. Yes. So that is also the part. Like as I said, that the statement is partial. It holds for slightly more general functions than continuous functions, but it need not hold for all bounded functions. Okay, so what does it mean? I mean that there can be functions f which are bounded for which this equality doesn't hold, okay, or doesn't make sense, okay, because you have to say that they are Riemann integrable and so on. So this need not hold. That means either they are not equal or it doesn't make sense, one of the three integrals over here. So one has to think of some example. All right, so I leave it to you. And we also define the triple integrals. So please write down the definition of iterated triple integrals first, and then write the statement of Fauven's theorem. So there's going to be an analogous, but there are going to be more combinations, because now you will have x, y and z. There will be 3 variables, so you have to change the order, okay. So I leave it as an exercise, okay. But what does it really tell you? Okay, so this is something very important. So this process, this is very intuitive. I mean, it's not out of the blue. It's like if you just look at what you are trying to do, and then you understand. So this was the picture. If you remember, we were trying to compute the volume of this solid, isn't it? So this Fauve's theorem, basically it tells us, let me just read it out a little bit. Okay, so this is the situation I have a continuous, okay, let us assume non-negative because it gives you a nice picture, continuous function on a rectangle, okay, and this is the solid S of which we want to compute the volume, okay. So this is the surface Z equal to f of x comma y. All right, so what we are doing in the Fauve's theorem, that we are fixing one variable and integrating with respect to other variable and giving us the quantity Ax. So look at this picture. If I fix an x, that means this point is fixed over here, and then y is allowed to vary, correct? So when I am fixing x here, that means I am going to get this piece, okay. So this is like I am cutting a cross section of this solid, okay. This is what the meaning of that fixing x and then integrating with respect to y. So if I integrate with respect to y from here to here, what I am going to get? I am going to get this area, okay. So this is a cross section of the solid, and then what we do? We integrate with respect to x. So we are going to integrate like all these. That means we are going to sum all these cross sections, and that is going to give me the volume, okay. So this is such a nice intuitive idea, that what you do, you look at you think of some big three-dimensional thing, and you cut slices, okay. So this is really that we are cutting these slices and then putting them or stacking them together, okay. And this process for nice surfaces, it perfectly makes sense. But when the surfaces are little bit difficult, then we have to worry about whether this cutting these slices and so on and then putting them together makes sense or not. So that is the whole idea of Riemann integration, okay. So when I do the other way around, I am cutting the slices which are parallel to the the xz plane, and then this is like fixing y first and then taking the integral in x. And so you are going to get a similar quantity a by over here, or the slices which are parallel to the xz plane, and then put them together. That means you are going to integrate further with respect to y. So this is a very nice, a natural, intuitive idea, that whatever solid you have got, you cut it into thin sheets and then put them together, because each sheet is basically, I mean, you think of this part Ax. This is the curve and this is domain, okay. So similarly over here, this is the curve and this is the domain. So what you are doing, that how to find these areas, because that is precisely the theory of one variable, okay. So the Fauve's theorem basically does this. It says that you cut these slices or these slices and then you just integrate them out, and you should get precisely the double integral, okay. So the idea is geometric, and the proof is little bit involved, so that's why I'm skipping the proof, okay. So you should see that the ideas they do not really come from just outside. It's there in the problem which you are dealing with. The whole point is that there are going to be technicalities in order to implement those ideas. So you have to justify all these steps, because we can say that that anything you cut it and then put them together, but mathematically does it make sense or not? That is what we need to worry about, because sometimes we may not be able to see how the surface of a given function is going to look like and so on. Okay, but for nice situations, this is a very beautiful idea which you can verify yourself. All right, so now we look into some problems of some surfaces and then some rectangular domains, and try to compute the double integral or the volume of the solid which is going to be given. All right, okay, so problems, sometimes they come in a different way, the wordings are different, so you have to figure out that what is the surface and what is the domain. Okay, and right now we have a situation which we can deal with is a surface, a continuous function, and a rectangle in the domain. Okay, so for example, they are asking us to find the volume of this solid which is bounded by this elliptic paraboloid. Okay, elliptic because this is 1 here, this is 2, correct? So this is a paraboloid, and the solid is bounded by this paraboloid, and this plane x equal to 2 and y equal to 2. Okay, and then the 3 coordinate planes. So first you have to collect all the data which is given here, because we have to understand that what is the problem. Okay, so one thing is clear, that this is z equals to 16 minus x square minus 2y square. This is the surface which is the paraboloid, and the domain. So basically what you do is you look at all these planes and see what is you are getting in the xy plane. Okay, so that is going to give you the so what I am saying, you have to decode the problem first, and then try to reach the double integral, because many a times you will realize that the half the job is done if you could figure out that what is the domain and what is the surface which you are talking about. Okay, so let us consider this. So this is the given surface, and please be careful, if I make a mistake, correct it. And if you look at the x equal to 2 plane and then y equal to 2 plane, okay, so and then the 3 coordinate plane. So basically the z equal to 0 is going to tell you that you are only interested in the part which is above the xy plane, and 3 coordinate plane, so x equal to 0 is also going to be there, and y equal to 0, so that is going to give you the limit of x and y, and they go up to 2 and 2. So the rectangle is going to be 0, 2 cross 0, 2. Okay, so this is the domain in your xy plane, and you are only interested in above this and below the surface given by this paraboloid. Okay, so now after a little bit of observation, you have a function and you have a rectangle, and volume, that is just going to be the double integral. Okay, so we write this volume is equal to the double integral, and write it this way. Okay, now this is what we wanted to compute, but we are trying to compute this. Okay, this we are able to do because of Fubini's theorem. Okay, we have to thank here the Fubini theorem, that it gives us this double integral in terms of these single integrals. Okay, now this is such a nice function, it's a polynomial in x and y. So you first integrate this guy with respect to x, 0 to 2, and then whatever you are going to get, you are going to get a function of y, you integrate with respect to y, that isn't it? So you just do this process, this integration, you can do better than me, and answer is coming out this one. Okay, but the main thing is this, that I am able to express my double integral in terms of these single integrals or iterated integrals. Okay, you see, if you had to use the definition, okay, some of you can try, just write down the definition, divide the rectangle into smaller pieces, and then find the values, because you can substitute x and y. Okay, so you can take some particular numbers, for example 0 to 2, you first divide it into 100 parts, so you know what are the smaller intervals, and similarly on the y-axis you can take and do that, and then see whether in using the limit you are going to get this. Okay, so this Fubini theorem and then the theory of single variable, it helps us to compute these integrals. Okay, and yeah, so one more example here. This is for triple integral. This is precisely the same idea. I mean, I should not be just reading it out to you, because you can do it. Here the problem is given in very straightforward manner. This triple integral is given and the box is also given. Okay, see, there are some small typos, I will correct them. So sometimes a question can also ask verify Fauven's theorem. That means you have to compute all the iterated integrals. Now when I say verify Fauven's theorem, in this case this is little tricky, because there are going to be several combinations here. Okay, so you can verify it for one or two, and just can see, because the function is nice. All right, so just compute this triple integral. So I am doing it in this order. You do it in one other order, like you first take dy and then dx and dz and so on. So please do all these problems, and I will take a break here, and then move on to situations which will require some generalization of the idea of this double integral which we just studied. Okay, so I take a break here. See you.